So in this module, we have a lot of optics problems involving mirrors and lenses. And for mirror and lens problems, we have the two same equations. It doesn't matter whether it's a mirror or a lens. We have that 1 over the focal length is equal to 1 over di plus 1 over do, the image distance and the object distance. We have that the magnification, which is the height of the image over the height of the object, is given by minus the image distance over the object distance. And for mirrors, we also have a relationship between the radius of the mirror and the focal length, that the radius is twice the focal length. So let's use these equations to first do a problem for a mirror. So we have a person 1.6 meters tall, is standing 3.2 meters away from a reflecting globe in a garden. So a reflecting globe in a garden is a circular ball that has a reflecting coating on it. And so a person is standing in front of it. They're 3.2 meters away, and they're 1.6 meters tall. So let's draw. So the person has a height of 1.6 meters. So that's the height of the object. So that's 1.6 meters. So we know HI. And they're standing 3.2 meters from the mirror, the globe. So they're the object. So the DO is 3.2 meters. Okay. And we're told the diameter of the globe is 18 centimeters, and we want to find where is the image of the person relative to the surface of the globe. All right, so let's analyze this a little bit. So I've got DO. I want to find DI. And so in order to use this equation to find DI, I need to then know what the focal length is. Do I know what the focal length is? No, but I'm told what the diameter is. The diameter is 18 centimeters. So I can use that and the equation R equals 2F to give me the radius. So if the diameter is 18 centimeters, then the radius is 18 over 2, or 9 centimeters. Okay, so if the radius is 9 centimeters, so then I have R equals 2F. So 9 centimeters is equal to 2F. So that means that the focal length F is 4.5 centimeters. All right, so now I know my focal length and I know DO. I want to find DI. So let's rearrange it to find it. Okay, so you know when you do a mirror problem or a lens problem, the focal length can be positive or negative depending on whether it's a concave or a convex mirror or lens. So for a mirror, let me draw just a cross section here. So a cross section of the ball, the person is standing on the outside of the ball, so to them it looks like a convex surface. So for convex, the focal length is on the virtual side, it's on the side where the light doesn't get to, so the focal length is negative. So when I put my numbers into the equation, I have to put that F is equal to minus 4.5. If I don't do that, I'm not going to get the correct answer. So let me rearrange this and solve. So I want to get DI, so I'm going to rearrange that equation there. 1 over DI is equal to, we're going to subtract 1 over DO from the other side. So it's 1 over F minus 1 over DI. Okay, so that means, so 1 over DO. So that means in order to get DI, I have to take 1 over each side, right? So that means DI is equal to 1 over F minus 1 over DO. And then I'm going to take 1 over that. So now put in my numbers. F is negative 4.5. And DO is 3.2 meters. All right, so now I've got to be careful because I've got, this is in centimeters, and my DO is 3.2 meters. Okay, so I need to put them in the same unit. So I can either put them both in meters or both in centimeters. Since I've already written this down, let's put them both in meters. So both in centimeters. So let's write that as 320 centimeters. And then I'll get my DI also in centimeters. Okay, and take 1 over that, and I get a negative number, negative 4.43 centimeters. Okay, if you'd converted it to meters, so if you'd put 1 over 0.045 minus 1 over 3.2, we would have got 0.0443 meters, and that would have been the same answer. All right, so there's my DI, and DI is negative. So what does a negative DI mean? That means that the image is virtual. It's on the far side of the mirror. All right, so it's 4.43 centimeters behind the mirror. And that's what happens when you look in the mirror in the morning in your bathroom. You see yourself looking at you from behind the mirror, so you're seeing a virtual image. All right, what's the magnification? The magnification is minus DI over DO. And we know both DI and DO, so it's minus negative 4.43 centimeters divided by DO, which is 320 centimeters. So be careful again, you got to keep them in the same unit. So since I worked it out in centimeters, I have to put DO in centimeters. So now the units cancel out. Magnification doesn't have any units. And you see here, I've got 2 negatives, so those 2 negatives are going to cancel out and make a positive. So I'm going to get plus a very small number, 0.01387. Okay, so why did I work this out? Well, it asked me how high is the person's image. So when the person's standing here, they're going to see a little image of themselves. Remember, a virtual image is upside right, so they're going to see themselves upside right. And of course, when you look in the mirror in the morning in the bathroom, you see yourself standing upside right, right? So it's a virtual image, it's upside right. And we want to know in part B, how large is the person's image? So what we want to know is what's the height of that little image of the person. So the height of the image of the person, remember magnification is height of the image over the height of the object. And now I've found the magnification. I know the height of the object, so I can find the height of the image. So the height of the image, if I rearrange that, is just the magnification times the height of the object. Okay, so the magnification is 0.01387, and it's positive, so that positive means it's upside right. The height of the object is 1.6 meters. Okay, so when I do that, I get a very small number, 0.0222 meters, or 2.22 centimeters. And again, I could have converted the height into centimeters and done times 160 centimeters and got my answer in centimeters doing it that way. All right, how do I know that the image is smaller and it's virtual, etc.? Well, I can also do my sketch using my special rays to do it. So let me just draw a quick image. So, oops, there's my lens. I've got my person who's standing over here. And then I'm going to draw my special rays. So let me draw my special rays. Remember, the focal point is behind the mirror over there. So special ray number 1 comes from the object, which is the person, and it goes in parallel and then bounces out. So it goes in parallel. I'm going to try and draw this on my whiteboard here, and I can't use a ruler or it moves the whiteboard, so you're going to have to put up with it being a little bit crooked. So it comes in like that, and then it bounces off so that it looks like it extrapolates through the focal point, because it can't really bend through the focal point. It can't go through the glass. So I just extrapolate that point out, and there's my special ray number 1. Okay, special ray number 2 is one that comes in like it goes through the focal point. Whoops. So it comes through the focal point, So it's like I would draw a straight line, and let me see if I can do that without a ruler. So it goes like that, and then it bounces back parallel. Okay, so there's my ray number 2. And I'm going to extend that backwards. All right. And ray number 3 hits the mirror at the center and then bounces back symmetrically. All right, or we can, well, let me just draw it that way. That's another easy one to do. So I do that. And see if I can draw it without a ruler. I need to go back relatively at the same angle that it came in at, and I extrapolate it backwards. And so I look and see, if I have my eyeball over on this side, my eye sees the green, the blue, and the red ray coming and spreading out. And so your brain interpolates those backwards and says, hey, that person is standing back on the far side and they're way shorter. So DI is negative because it's virtual, and the height of the image is much smaller. And you can also just remember that if it's a convex lens, it's going to be always virtual. So a convex mirror, always going to be virtual, and it's always going to be smaller. This is like the passenger side mirror in your car that says objects in the mirror are closer than they appear. And you know, if you look in your passenger side mirror, you always see the cars in the other lane. You always see them as being upside right, right? They're not traveling along upside down. So they're virtual, smaller, and upside right.